Hi, I'm John Anderson, and this is enhanced content for Common Engineering and Technology courses, Module 5. In Module 5 and 6, we're going to do an introduction to composites, where we talk about the basic materials that we're going to use, how we put those together, and how we come up with fiber reinforced composites. We'll talk about fiberglass, which is a lower performance type of fibrous composite, and we'll talk about aerospace applications on the higher end. So, without further ado, let's get started. Introduction to composites and aerospace manufacturing. The first slide in this module is just a course overview, and you can see we start from the basic materials, the building blocks, and why we're going to use composites. And we go into some simple manufacturing techniques. So we're going to do composite material structure, that is, how do you put it together, composite material components, aluminum versus composites, because aluminum is very important in aircraft design, and composites have taken over a lot of the applications for aluminum. The advantages and disadvantages of composites in aerospace, some composite applications, composite manufacturing techniques. So this is the break between Module 5 and Module 6. We're going to stop today, or in this module rather, at composite applications, and we're going to take up composite manufacturing techniques in Module 6. That's a pretty good break, and that's not unrealistic, a break if you were actually going to do this in a regular lecture environment using these materials, using these slides as they are. So, what are composites? Composites are combinations of different materials which yield a product with superior properties, superior to either of the individual components that we're going to put together to form this composite. Composites have been around a long time. Composite armor was actually used by the Greeks in antiquity. And there's an interesting History Channel film that's on YouTube that I'm going to bring up a part of now.
Within the later periods, people had to hear what was going on.
In response to the developing arms race, Greek metallurgists needed to construct armor that withstood the deadly firepower that was now developing on the battlefields. One innovation used composite materials in an ingenious system to protect warriors in combat. Incredibly, the armor consisted of a high-intensity fiber material that Greek engineers designed to withstand metal-tipped arrows.
What we've got here is a liner thorax, a lin thorax, which is made up of layers of linen glued together. In fact, this one's got 14 layers of linen with a leather core in the middle. It's lighter than metal armour. It moulds itself to your body when it's warm, but it is very, very hard and very, very protective. In many ways, it's akin to modern Kevlar body armour.
We used a composite bow at point-blank range to test the strength of Linathorax technology.
Oh, that'll hurt. Well, I'm actually quite pleased with that, because that was at point-blank range. Remember, this is only cloth that's stopping this arrow. So at a normal combat range, I think that's about the best they could expect for. The fact it punched through, lucky shot.
Despite using a composite bow with a draw weight of 160 pounds, hitting at 90 miles per hour, only the tip of the arrow has penetrated.
So as we can see, they've what the Greeks were doing was using a laminate of linen and leather or other materials that would form a barrier. It's very, very similar to the way Kevlar is used now in soft ballistic vest or ballistic armor. So modern composites, or advanced composites, as they've been referred to, are typically fiber reinforced plastics. What does that mean? Fiber reinforced plastics, or FRPs, consist of at least two materials. They consist of a plastic which binds the fibers together, and this is also called a matrix. And they have fibers, typically small in diameter and long in length. There are two types of fibers. There's short fibers that are sometimes referred to as staple fibers, and there's long fibers. These fibers are typically on the order of 5/10,000ths of an inch in diameter. The staple fibers, the short fibers, are typically around a ½ inch long. And we're going to be using a lot of these terminologies like staple fibers. These actually came from the textile industry because a lot of the composites manufacturing techniques look a lot like making cloth or making woven materials. So these long fibers are typically laid into a mold in place, and they're combined with the matrix. The short staple fibers can be handled in other machinery. For instance, there's a lot of injection molded nylons that have glass fibers embedded in it. And the glass fibers in there act sort of like rebar does in concrete. So you can get improved properties over the nylon, both in thermal resistance properties and in tensile strength, by embedding these glass fibers. And you can still process it in normal plastics processing machinery. In general, the matrix imparts toughness or crack resistance, and the fiber imparts ultimate tensile strength. So this is a simplified illustration of a fiber reinforced plastic composite. So the green that you see here is the matrix material, and the black cubes are the fibers. In this case, all of the fibers are laid in one direction, as you can see, and the matrix holds them together and in place in relation to the other fibers. So if we apply a tensile strength, I'll tell you, we'll talk about this in a minute, but I'll tell you now that the fibers are much, much stronger in tensile than the matrix material is. So if we apply a tensile strength along this end, pulling outward like this, along the length of the fibers, we get a very high tensile strength. We get a very high resistance to deformation. On the other hand, if we pull in this direction, perpendicular to the lay of the fibers, we get a much lower resistance to deformation, because all we're pulling against is just the plastic matrix itself. So the function of fiber is to carry the load. Typically 70 to 90% of the load carried in a composite material is carried by the fibers. And it provides structural properties to the composite: stiffness, strength, and thermal stability. And it also can provide electrical properties, either conductivity or insulation. So if we put in fibers that conduct electricity, we can do things like make a composite fuselage more resistant to lightning strikes. So we can allow the current from the lightning strike to drain out of the fuselage of the airplane. On the other hand, Cessna, in an effort to improve the performance of their aircraft in the Cessna, I think it was the 350/400 models, they wanted a very smooth fuselage. And so one of the ways they attain that is to get rid of the external antennas. They put the antennas, the radio antennas, the avionics antennas, inside the fuselage of the aircraft. Well, in order to do that, you need to be certain that you have non-conductive materials over the radio antennas, or you'll essentially negate the antennas. So we do composite materials, or they use composite materials over these areas in the fuselage where the antennas were mounted that were electrical insulators. And I think we talked about in materials, one of the properties of plastics, of just the resin material that holds these fibers together, is that they're typically non-conductive. So whatever conductivity we're going to get out of this composite material is going to have to come from the fibers. So the function of the matrix is to bind the fibers together to hold them in place, provides rigidity and shape to the structure by holding the fibers in place. It isolates fibers to slow crack propagation. So if you think of the illustration that we used before, and you're pulling on these fibers, if one of the fibers breaks and you didn't have the matrix material there, the load from the fiber that broke would be immediately transferred to the other fibers. Well, the matrix material takes up some of that strain from the broken fiber in itself. So it acts as a damper sort of on the shock of having that broken fiber in the bundle. The matrix also allows us to get improved surface quality because we can mold this matrix material smooth on the outside, or we can put the surface of that matrix material against a mold face that we have polished. We can get a very nice, smooth surface on it. It provides corrosion and wear protection for fibers. In other words, it seals the fibers up from the elements. If we look at the relative strength of the fiber versus the matrix, you can see this diagram is stress versus strain. So stress is force per unit area. So for a certain force here, we can see that we get a lot more strain in the resin than we do in the carbon fiber. Actually, let's pick a lower stress point here. So we get this much strain with the resin, but we only get this much strain for the carbon fiber for a given force. So what does strain mean? Strain is a deformation. It's how much you stretch this material per unit length, per original unit length. And it's measured in inches per inches. Inch per inch, rather. So we can see that as we increase the force on this carbon fiber, we don't get much stretch. We don't get much elastic deformation here. So it acts in a brittle fashion. But it can withstand high stress loads, high forces on it. The resin, on the other hand, as we increase the stress on it, it stretches a lot. So this tends to take up some of the strain on the fibers, and it allows us to have some impact resistance here. Well, if we go back to this simple diagram that we had, we can see that all the fibers are in one direction. So as we said, if we put force in this direction, we get a very weak material. It stretches, it deforms a lot. Put force in this direction, we get a very strong material. What if we want to have strength in several directions? Well, what we can do is build up plies of fibers so that the fibers are oriented in different directions as we build up the stack. And thus, we have strength in more than one direction. So what do commercial fibers actually look like? Again, we're going to use some of the terminology that came from the textile industry. If we take a roll of fibers and we take a bunch of individual fibers and we twist them together, we call that a yarn. And so this is multiple fibers twisted together. If we're talking about carbon fibers and we take many yarns and twist them together, then we end up with a large bundle of carbon fibers, and we refer to that as a tow. And this may be several thousand fibers in the tow. And this looks like a string or a rope. If we're using fiberglass or glass fibers, and we have large bundles of several thousand fibers, we call it a roving. So it's a different terminology depending on whether you're using carbon fiber or fiberglass. So if we take these fibers and we lay them in a stack, a thin stack that's either unidirectional or woven or multidirectional, we can have a thin or a relatively narrow roll of material that we call tape because it looks like a tape. Or we can make a much bigger piece of material that's called woven fabric or mat. So this is some of the configurations that we can get in tape or mat. We can have a plain weave that's an alternating. You can see let's talk about fiberglass. You can see the rovings here, and they're in a plaid fashion, checkered fashion. So it's sort of a basket weave, I guess, is one way of thinking of that. And then we have different configurations depending on how we want to distribute the force in this mat. And this comes from one of the major suppliers of composite materials, 10K Composites. I think it's important, the reason I mentioned the manufacturer here, and you'll see in the student activities, I'll have you go to some manufacturers' websites. I think it's important that we start introducing students at the undergraduate level to what actual materials look like. Although most of the time when we teach theory, we idealize the materials, students need to have a feeling for where that idealization breaks down. My personal opinion. So composite fiber materials, common fibers that we use in composites are glass fibers, or which is called fiberglass. This starts out as silica sand. It's run through a glass making process where you end up with molten glass at high temperature that you extrude through a small orifice to get this glass fiber, and then you quench that. This comes in a couple of different grades. Typically, the tensile strength of fiberglass is between 3.5 and 4.5 gigapascals. The cheapest fiberglass costs about $1 a pound. And these numbers are a few years old, but relatively the cost is the same. The higher tensile strength, or S-glass, typically runs about $8 a pound. So, what else do we have here? We also have carbon fibers. Carbon fibers start out as a polyacrylonitrile fiber that is burned up essentially in a furnace at very high temperatures, and you end up with through a process you end up with carbon. There's also some other materials out there, primarily aramid materials. Aramid materials are cousins to nylon. They're a polymer material. The name comes from the fact that the molecular chain, which is the backbone of this polymer, contains both an amide and aromatic groups. And this, because of the mechanisms, because it contains both of those, and because of the mechanisms of entangling those molecular chains, you end up with an overall material that has a fairly high tensile strength and a fairly high melt point. The DuPont materials Kevlar and Nomex are both aramids. Kevlar, as a point of reference, has a tensile strength of about 2.8 gigapascals and costs about $30 a pound. Both of these are petroleum derivatives, and so they're tied to the price of oil, of course. Talking about tensile strength, carbon fibers only have a tensile strength of about 2.6 gigapascals. And so that's sort of on the low end of where you have glass fibers. Carbon fibers are much more expensive. So why? Why would we use carbon fibers? Well, when we form these fibers, the fiber diameter for carbon fibers are about half that of glass, but they have about 70-80% of the tensile strength. So we can use less material, less of the fibers, and we end up with a very light, strong material. So the types of plastics or resins are the types. When we refer to plastics in the matrix, we typically refer to them as resins. Plastics are polymer materials. The thing that makes them polymers or plastics is that they have long chain molecules. Long chain molecules. It's the difference in how we make up these chains that gives us different properties in the plastics. There are two basic types of plastics. I think we talked about this in materials, based on how these molecules are bonded together. Thermoplastics, in thermoplastics, these base chain molecules are not chemically bonded one to another. They're not cross-linked. And so they're held together typically by mechanical interference between the polymer chains and by van der Waals forces or secondary bonding, which is similar to gravity. So if we get two bodies close together, they have a mutual attraction. Well, these molecules are small, but they're very, very close together. And so we get an attraction to each other that's similar to gravity. But we can break those secondary bonds and then bring the molecules back into proximity of each other and reform them. So that's why thermoplastics can be melted and then cooled and resolidified, and you have very close to the same bulk properties that you had of the original material. And you can do this several times with thermoplastics. Ideally, you could do it an infinite number of times, but in fact, as you heat up and cool down the thermoplastics, you damage some of the long chain molecules, and this damage accumulates over a period of time. So, thermosets, on the other hand, these long chain molecules are cross-linked. That is, they are tied together with molecules that are chemically bonded to adjacent long chain molecules. So, what happens there is that once you solidify, once you form that cross-link, once this thermoset solidifies, you can't remelt it. You can't, as you raise the temperature, you can't break those chemical bonds between the chains, or when you do, you're breaking the backbone of the chains at the same time. So you end up charring, typically you end up charring a thermoset rather than melting it. Common thermoset plastics used, and most of the resins in the matrix materials are thermoset plastics. So typically the thermosets used in high-performance composites are epoxy, polyester, phenolics, cyanate, esters, BMI, because it's too hard to pronounce the other, and polyimide. And this sort of goes up in performance as we go down this list. Polyimide is very expensive and is used in very high performance carbon fiber composite materials, typically. It's has a very high melt point or a very high upper limit of thermal resistance, I should say. And it has a pretty high tensile strength also for matrix material. There are thermoplastics that are used in composites. Typically they're nylons or nylon's a fairly high performance thermoplastic, or PEK, polyether ether ketone. PEEK is used like polyimide in a very high performance, higher end of composite materials, and in those applications where you specifically need to have a thermoplastic instead of a thermoset. So, how did composites take such a bite out of aluminum for aircraft construction? Well, let's look at the pros and cons of aluminum versus composites. Aluminum is an isotropic material. That means that it has the same properties in all directions. So if I take a block of aluminum and I pull on it in any direction, I should have approximately the same tensile strength, for instance. It should respond to external stimulus approximately the same in any direction. Composites, on the other hand, are anisotropic, which means they have different properties because of the direction of the fibers. We saw how that worked. Composites are built in layers called plies that are stacked up or laid up to form a laminate. And each layer has fibers that run in defined directions. Because of the layers, the properties are different in plane or through the thickness. So some advantages of composite materials over metals in aerospace: they're very lightweight. Their resistance to corrosion. If we're using carbon fibers and we're joining that to metals, we can get a corrosive reaction between the carbon fibers and the metal. So one of the things the matrix does for us is to seal up that interface. We have high resistance to fatigue damage in composite materials. We have reduced machining because we can form this material we can mold this material to near net shape, or almost to the shape that we need in our final part. We can easily make tapered sections and compound contours. Sometimes that's a problem in machining out metal. We can orient fibers in direction of the strength and stiffness needed, so we can put the mass of our part in such a way that we have an efficient use of that mass in giving us strength. It's possible to reduce the number of assemblies and reduce fastener count when we co-cure, that is, take two fiberglass or two composite parts, and we cure them together, or co-consolidation is used. And we'll see a slide, a couple of slides down, that talks about a study that was done on the L1011. We'll highlight that. We can absorb radar microwaves by the way that we make the composites, so it can add stealth capability. The thermal expansion of composites is close to zero, so it reduces thermal problems in outer space applications. Interesting picture here. This is an aircraft wing section from a small company in Bend, Oregon. Started out making kit airplanes. It was called Columbia Aircraft. I think they're still in business. Then they started making completely assembled aircraft, and to illustrate the strength of their aircraft, this is a complete composite fuselage aircraft, they parked a Lincoln Navigator on top of the wing box to look at the deflection. And you can see this Lincoln Navigator is supported by the wing structure mounted on these concrete sawhorses or platforms out here. Some disadvantages of composites over metals for aerospace. Corrosion problems we mentioned before can result from improper coupling with metals, so that you get a reaction between the carbon or graphite and the metal. We have degradation of structural properties under temperature extremes and wet conditions. This happens with thermosets. This is mainly a phenomena of the matrix itself, a matrix resin. It happens some with thermosets, but it's more pronounced with thermoplastics. When you get high temperatures and a lot of water available, you get oxidation of the plastic material. So you get a breakdown of the polymer chains, and you change properties. It tends to make polymer materials brittle and form cracks. We get poor energy absorption and impact damage from composites. We may require lightning strike protection. We talked a little bit about that. It has expensive and complicated inspection methods. I think we mentioned this when we were talking about quality control. When we lay up these plies of fabric for our composite material, for the stack up, if we end up getting a bubble in there or void, when the matrix material cures, that void still is in there. And so over time, that can cause a delamination of the stacks, of the laminates. And that's not a good thing. Those are very hard to spot. There are techniques out there. There are new techniques being developed daily, but it's very expensive, and it's very complicated. It's hard to do. And reliable detection of substandard bonds, that is, part to part, is difficult when these are cured together, co-cured. Well, let's look at this design study I mentioned before. This was done for the L-1011 aircraft, Lockheed 1011 aircraft, which was a commercial airliner. I think for the most part, these are out of production now or out of service. You may find one every now and again. This was the first commercial aircraft that they considered using composites in a big way. And there were actually design studies done. And so this is for a couple of parts. One is for the inboard aileron. The aileron is a control surface on the wing that allows the aircraft to bank one side to the other. So the aileron is a fairly small component. This is a big passenger jet. Size is on the order of a 757 or large 737, I guess. So these ailerons, the aluminum aileron weighed 141 pounds, composite 104. So we had a little bit of a weight savings there. The number of ribs inside, remember we talked about construction of aircraft, and we talked about the ribs supporting the skin of the aircraft. So the number of ribs necessary for an aluminum construction versus a composite construction was down for composites. Less ribs means less joints, means less material, less assembly. So the number of total parts that you need to assemble the aileron, if it's made out of aluminum, was close to 400, and it was only half of that number of parts for composites. The number of fasteners, likewise, was about half for composites. Each of these fasteners has to be fastened. It has to be assembled. So if you're using bolts, for instance, you think about the whole process to put in a bolt. You've got to drill the hole. You've got to deburr the hole. You've got to insert your fastener, and then you've got to tighten your fastener down in some controlled fashion. So there's a fair amount of labor associated with doing fasteners. If you can cut the number of fasteners in half, that's a pretty big hit. They also did the vertical fin box. So this is a larger component, 858 pounds in aluminum, 623 in composite. The number of assemblies for this went from 21 down to 15. The number of parts went from 714 to 229. So this is about a third of this. That's pretty good savings. The fasteners went from 40,000, a little over 40,000, almost 41,000 actually, down to close to 10,000. So you have 25% of the fasteners. So this offers a tremendous savings. And if you're going to do one or the other, you of course pick the low-hanging fruit. This is going to give you the biggest bang for your buck. This is composite usage on a Boeing 777, or 777 as it's referred to. You can see there's a fair amount of pieces here that are composites manufacturing. The 777 was the first commercial airliner to have a considerable number of parts, composite parts designed in. And if we look at composite component content, then we have versus our time frame. So this is percent of composite components by structural weight versus the year. So we can see right around in here, well, let's start here. From 85 back, we had 10% or less of components, very, very few components that were composite. And then in the period from 85 to 2000, you started to see a significant number of, a significant amount of composites added into commercial airliners, with Airbus sort of leading the charge here, up at around 15% for their A320, A330, and A340. The Boeing 777 was down around 10%. And then as we go out in time, we see some things happening here. The Boeing 747 is a legacy airplane. So what they did was, if you look over here at the Boeing 747 back in 65, excuse me, when it first came out, very, very few composite parts. And then in 2010, a fairly significant increase in composite parts. So these are retrofitted parts. Around the same time, we see the A380 start to have a fair amount of composite parts, approaching 25%. And its competitor, the Boeing 787, is up around 50%. So this is the current state of the art for commercial airplanes. And you can see it seems to plateau here with Airbus and Boeing. There are aircraft on the drawing board right now that are Boeing 737 class replacements, A320 Boeing 737 class replacements. And they're essentially following this same pattern of the 787.
Okay, that completes our presentation for Module 5. And we'll continue this introduction to composites in Module 6, where we'll talk a little bit about the practical applications, or rather the practical methodology to go about putting these materials together. Please go to the student activities now for Module 5 and complete the work there, and I'll see you on Module 6.